All right, today we're talking about a source of power it's as old as civilization itself, but it's also at the absolute cutting edge of our energy future. We're diving into wind energy.
So here's the big question, right? It sounds simple, but the answer, man, it covers centuries of incredible innovation. How do you take something you can't even see
And somehow turn it into the very electricity that lights up our entire world? It's a fantastic question, so let's get into it. To really get where we are today with these giant turbines, we've got to go way back. Because this whole idea of harnessing the wind, it is not new. Not even close. The whole story really kicks off in ancient Persia. And forget electricity, they were just trying to do something basic, grind grain. From there, the idea moves and evolves through the Middle Ages in Europe, and eventually you see it become this iconic symbol of the American West. I mean, for rural folks back then, these windmills were everything. They were literally pumping the water that kept them alive. And you can really see a huge design shift here. On the left, you've got those early Persian mills. They used a vertical axis, kind of like a spinning top. But then look at the right. The European mills introduced the horizontal axis, more like a pinwheel. Now, this design was definitely more complicated to build, but wow, it was a massive leap forward in how much work you could get done.
So for hundreds of years, wind power meant one thing: mechanical work, pumping, grinding, that kind of stuff. But then a completely new kind of power comes along and changes the entire game, giving this ancient tech a totally new mission. The first baby steps in the 1890s were pretty simple, really. People were basically just bolting generators onto old windmills. Fast forward to the mid-20th century and you could actually buy systems designed just for electricity. But here's the crazy part. The very thing that was supposed to be progress, the big central power grid reaching everyone, it almost made personal wind power go extinct for decades. So what brings it roaring back? The 1970s OPEC crisis. That was the spark. All of a sudden, you had this perfect storm, right? You've got intense economic pressure, a desperate need for energy independence, and this new growing environmental movement. It was the exact combination of things needed to kickstart the modern wind power industry. But listen, to go from those early experiments to the absolute giants we see dotting the landscape today, engineers had to get the science right. They needed to figure out the fundamental recipe, the secret sauce for turning invisible, moving air into cold, hard, measurable power. And it all starts with a concept you probably learned in high school: kinetic energy. Basically, if something's moving, it has energy. Simple as that. So you have to imagine the wind as this huge, invisible river of energy just flowing all around us. And it's all about the mass of that air and, crucially, how fast it's moving. Okay, so we have energy, but the next piece of the puzzle is power. See, power isn't just about how much energy is out there, it's about the rate you can grab it. It's the flow. So the real question for an engineer is, how do we calculate the actual power that's available in the wind at any given moment? Well, it turns out it comes down to just three main ingredients. First, you've got air density, how thick the air is. Second is something called the swept area. Just picture the giant circle the blades make as they spin. That's it. And third, the big one, the real superstar of the show, wind velocity, how fast it's blowing. And when you put all those ingredients together, you get this. This formula is the recipe. It tells us that the power you can get is 1/2 times the air density times that big swept area times the wind's velocity cubed. Now, look closely at that equation, because the really crucial part, the detail that changes everything, is that last little number, velocity cubed. This is the whole ballgame. Let me put it this way. If you double the wind speed, you don't just get double the power. No, you get 8 times the power. It's the difference between a little shove and a knockout punch. And that is why finding the windiest spots on Earth is so incredibly important. Okay, so once engineers had this recipe, this powerful equation, the mission became crystal clear. Design machines that could push every single one of those variables to the absolute max. And people tried all sorts of crazy designs, believe me. But in the end, one clear winner emerged for making power on a massive scale, and it's the one you see everywhere, the 3-bladed, upwind, horizontal axis wind turbine. Upwind just means the blades are facing the wind, in front of the tower. It just turned out to be the best possible mix of efficiency, stability, and, not costing a fortune to build. And wow, this just says it all, doesn't it?
This is how engineers tackled the A in that power equation, the swept area. I mean, just look at the scale of these things. We went from turbines that were, what, the size of a big house, to absolute monsters whose rotor diameters are longer than a jumbo jet. Bigger blades mean a bigger circle, a bigger swept area, and that means you're grabbing way, way more power out of the exact same wind. And don't think for a second that these are just simple blades on a stick. No way. Inside that box at the top, it's called a nacelle. It's packed with incredibly complex machinery. You've got a massive drivetrain, a gearbox, and of course the generator. The whole job of that system is to take the slow, heavy, powerful turning of the blades and convert it into the super fast spinning that you need to make electricity. But here's the thing, even with all this amazing engineering, you can't cheat the laws of physics. It turns out there are some very real, very hard limits on how much power we can ever hope to get from the wind.
Okay, so I'm just going to put a number on the screen. 59%. What on earth could that mean?
That number represents something called the Betz limit, and it's basically a hard stop sign put up by physics itself. What it says is that the absolute theoretical maximum efficiency of any wind turbine is just over 59%. You're probably thinking, wait, why not 100%? Well, think about it. If you took all the energy out of the wind, the air behind the turbine would completely stop. It'd be like hitting a solid brick wall. Air would just pile up and go around it. To keep the air flowing through the blades, you have to let some of that energy go.
Okay, now for our next number, roughly 30%. That's a lot lower than 59, isn't it? This number gets us out of the world of theory and into the reality of how these things actually work day to day. This is what's known as the capacity factor. Here's the deal. The wind isn't always blowing at that perfect ideal speed. Sometimes it's too slow, sometimes it's too fast. So a turbine almost never operates at its peak rated power. The capacity factor is the number that tells you what it actually produced over a whole year compared to what it could have produced if it ran full tilt 24/7. It's a super important number for figuring out how much power you're really gonna get. So there you have it. We've gone from ancient mills grinding grain to these incredible modern giants, engineered to push right up against the very limits of physics. It's been a wild journey, and it really just leaves us with one big, fascinating question to think about. Where is the wind going to take us next?